The next chapter we're going to deal with is radicals. Radicals are formed during a homolytic bond cleavage, so this is a different type of reaction mechanism than we've seen in all of the previous chapters. In a homolytic bond cleavage, we have a bond, and instead of breaking where both of the electrons from the bond go to one atom, they're actually split. One goes to one atom, one goes to the other. Notice these arrowheads are different than the arrowheads we've drawn for other reactions. So instead of being a double-headed arrow, these single-headed arrows represent a homolytic bond cleavage. So this bond will break just as we're used to, but instead of having a lone pair on one of these atoms, we now have a radical or a single electron on each of these two atoms. If we're thinking about the geometry of radicals, they are essentially trigonal planar. Radicals in a lot of ways mirror carbocations. So if we take this methyl radical CH3, another way of drawing that is in a trigonal planar fashion where we have a p orbital, which would be empty in the case of a carbocation, but in this case it has a single unpaired electron. Radicals, because they mimic carbocations, actually have the same trends in carbocation stability. This methyl radical will be the least stable of all the radicals we can make. Now let's take a look at the structure and see why. If we are losing electron density, basically we would want to have 8 valence electrons, in this case we only have 7, we need to find another source for some extra electron density. In the case of a methyl radical, all of the hydrogens are out of plane with the methyl radical itself, that p orbital. Let's take this a little bit farther and we add another methyl group, so now we have an ethyl radical. If we take a look at this structure, we've got our p orbital again, which has an unpaired electron in it, but the methyl group here, this overlap in this sigma bond, can actually donate some electron density into that p orbital, which can help stabilize it. This is hyperconjugation like we saw with carbocations. So if this is the least stable, a primary radical is more stable. A secondary radical is even more stable because we have two sources of hyperconjugation, and a tertiary radical will be the most stable. And again, just like carbocations, resonance structures can also be drawn for radicals. So if we have this benzylic radical here, it's actually very stable. The reason that it's so stable is because it has resonance stabilization. So this radical can donate into a bond. This double bond here, this pi bond, can break and donate an electron to help form a new pi bond. The other electron from this pi bond will shift here to this carbon, which will give us this new radical. Resonance can continue around the ring. We can make a new bond here and put the radical on this next carbon. And we can make another resonance form where this radical helps form a new pi bond here, and we get the formation of the radical on this third site here. So essentially we have 4 resonance forms where this radical moves to different carbons. And because the loss of electron density, or the lack of electron density that we see in the radical, is distributed across the molecule, it's actually going to be relatively stable.